Okay, everybody, grab your headsets. Grab your headsets. You got a headset? Yep. All right. Yeah, I know. Is it live? Yeah, okay, great. Good evening. I'm Jim Green. I'm NASA's chief scientist, and I'm just delighted you've been able to stick around this late because we have a real treat in store for you. A fantastic scientist, Yasef and Yamba, has been doing research using satellites that NASA has in the area of climate, but also linking that to vector-borne diseases. I mean, when you think about it, it's absolutely amazing what we can learn with satellite observations when we bring in environments that mosquitoes and flies, those pests in the environment that does carry diseases, these vector-borne diseases that show up in the population. So he's a scientist at the Goddard Space Flight Center, has been working there for many years and has done a fantastic amount of research. So let's hear from him. And then our climate advisor is also here, Gavin Schmidt, and we'll be available to answer any questions you may have. All right? Thank you. Let's let her roll.
Research scientist at Space Flight Center. Next slide. My research and application work involves exploitation of data from NASA's Earth observing systems to understand the climate drivers of ecologically coupled vector-borne and zoonotic diseases. Such data sets as shown on this slide include long-term measurements of sea surface temperature, rainfall, vegetation, and land surface temperature. The mix of these observations allows us to understand how variability in sea surface temperatures influences patterns of rainfall and temperature and other variables globally, and consequences on the land surface through patterns of floods and droughts, which in turn lead to disease outbreaks. Next slide. One aspect of climate variability that we pay special attention to is the El Nino Southern Oscillation. This is an internal mechanism of the climate variability which can be traced back to over 500 years. It is defined by the anomalous warming termed El Nino and cooling termed La Nina, ocean temperatures in the eastern equatorial Pacific, as shown in red and blue on the ENSO index in the graphic on the top left. These changes in ocean temperatures are coupled to atmospheric circulation. Now, due to the sheer size of the Pacific Ocean, these variations have downstream impacts on patterns of rainfall, temperature, and other variables across the world. The remote connections are termed as teleconnections and illustrate how Earth system components are connected. The two maps at the bottom illustrate the typical rainfall response patterns across the world during each of these events, either La Ninas or El Ninos, with some regions receiving above normal rainfall and others experiencing drought patterns, with consequences to disease outbreak patterns globally. Next slide. A good illustration of these patterns is the recent 2015-2016 El Nino event. The two maps on the right show sea surface temperatures anomalies at the top and rainfall anomalies at the bottom during the peak period of this El Nino event between December 2015 and February 2016. Working with the interagency partners, including Defense Health Agency, USDS Center for Medical, Agricultural, and Veterinary Entomology, and non-governmental partners, including International Society for Infectious Diseases, ICID, and EcoHealth Alliance, we were able to gather in real time disease outbreaks that occurred during this El Nino period between May 2015 and April 2016. The map on the right shows the various disease manifestations around the world, including a huge cholera epidemic in Eastern Africa, dengue in Southeast Asia, dengue and chikungunya in Central and South America, plague and hantavirus outbreaks in southwestern United States. What we learned from this process is that variations in patterns of rainfall, flood and drought, temperature and vegetation conditions favor the emergence and increase in populations of different disease vectors, including mosquitoes and rodents, therefore amplifying or triggering epidemics of human and animal diseases that can persist for months or years if not controlled. Next slide. The following animation illustrates how we can tie together these ENSO events, showing variations in sea surface temperature with patterns of disease outbreak globally for the period 2009 to 2018. On this animation, warmer than normal sea surface temperatures are shown in brown shades, and colder than normal temperatures are shown in shades of blue. You can notice the sharp elongated structure of El Niños and La Niñas in the eastern equatorial Pacific Ocean. The ENSO index shown at the bottom of the visualization enable us to track and identify El Niño and La Niña periods. Different colored dots on the land surface represent locations of disease outbreaks, with clusters showing possible epidemics of a given disease. Next slide. Now, digging deeper, we can look at what was happening in Southeast Asia during this 2015-2016 period. This animation shows the influence of patterns of rainfall variability that resulted in dengue outbreaks in Southeast Asia. Green shades show areas of above normal rainfall, brown shades show areas of below normal rainfall, and the purple pins show locations of dengue outbreaks. Warmer than normal temperatures during drought periods tends to increase the populations of Aedes mosquito species that transmit the dengue virus in densely populated urban environments. The plot at the bottom is an index of rainfall with the number of locations reporting dengue activity between January 2014 and December 2016. We can be able to track the emergence of the disease activity as the drought persisted over Southeast Asia, the peak conditions of the disease activity, and the recession in concert with the rainfall anomaly patterns against the background of this 2015-2016 El Nino event. Next slide. This following animation shows the sequence of monthly satellite vegetation, normalized different vegetation index for Africa and the Arabian Peninsula from 2015 to 2016. We use this index as a proxy to infer habitat conditions that are suitable for emergence of mosquito vectors of Rift Valley fever, a zoonotic disease of livestock and humans. Positive anomalies are shown in the gradients of green colors associated with periods of above normal rainfall, while shades of brown are associated with lower than normal rainfall and an indicator of drought periods. Brown pins on the map indicate locations where Rift Valley fever outbreaks were reported that occurred in association with greener than normal or above normal rainfall conditions. One important revelation from this work is the tendency for Rift Valley fever outbreaks to occur in Eastern Africa during El Nino events, for example, in 2006 and 2007, and over Southern Africa during La Nina events, for example, during the period 2009 to 2011. This is a clear illustration of how climate variability induced by El Nino teleconnections has an influence on disease outbreak patterns in different regions. The outbreak of Rift Valley fever in 2018 between March and June doesn't follow this particular historical pattern and indicates the increasing role of climate extremes in a changing climate can have on unusual disease outbreak patterns. Next slide. Now, equipped with this knowledge and research that we have done on various diseases, we are working with several partners to create a big data disease risk mapping and forecasting models, combining disease outbreak information from PROMED, Pan American Health Organization, and Defense Department, and also human population density and mosquito vector distributions that transmit the disease Chikungunya. We combine this with dynamic satellite data inputs from NASA and NOAA to generate forecasts. So slide 9, next slide, is a good example of this activity, showing the global chikungunya forecast system that is now providing forecasts of regions at risk of chikungunya activity up to 3 months in advance, with associated information on trends in outbreak patterns to enable PAHO and DoD and other public health agencies elsewhere to undertake prevention and control measures early enough to reduce the burden of chikungunya vector-borne disease. Next slide. All this information is combined together in an application that we are calling ChikRisk app. This is open and publicly available for use. This work is enabled through the support of NASA Applied Sciences Health and Air Quality Program, Defense Health Agency, Defense Threat Reduction Agency, NOAA's International Research and Application Program, and executed in collaboration with NOAA Climate Prediction Center, USDS Center for Medical, Agricultural and Veterinary Entomology, International Society for Infectious Diseases, PROMED Global Disease Surveillance Efforts, EcoHealth Alliance, and Pan American Health Organization. Thank you.
Let me invite Gavin up and be happy to answer any questions you may have over this talk or anything else you'd like to know about some of the activities that NASA is doing in making global observations available and their interpretation in the area of climate change. Yes, sir. Yeah, go ahead.
What do you see as the next leap forward? What do you see as the next leap forward technologically for remote sensing? Or maybe there's some things in the works that you can tell us about.
Well, one of the things that NASA does, of course, in its climate program is indeed develop a variety of advanced sensors. And once they start making routine observations that are important, then they end up being weaved into long-term observations. And then, of course, NASA participates in the building of satellites for NOAA, and then that ends up being the long-term record. But there are several measurements, in the area of like aerosols, methane, more methane measurements, that need to be done as we look at more of the greenhouse gases. Gavin?
So what we can detect from space is basically anything that's in the electromagnetic spectrum and anything that is associated with any of the other forces that are large. So gravity, we can measure gravity from space, and we can measure all the different lines in the spectrum. And those have fingerprints that are associated with all sorts of different things that are happening on Earth, and we're learning more about those all the time. So looking at the difference between certain frequencies allows us to say something about the health of vegetation. Looking at the angles by which light is refracted allows us to say something about the composition of aerosols. And we've been trying to get good aerosol measurements from space for a long time, and we haven't been able to do it for a number of either programmatic or just like bad luck reasons. So we had one sensor that failed to make orbit and is measuring aerosols at the bottom of the Pacific Ocean, unfortunately. But we have a new satellite that's coming up, PACE, that will be looking. That has a polarimeter that's going to be looking at aerosol composition as a way of getting at what's going on at the ocean surface. And so, looking at all of those. Oh, that was good. Who did that? That was well done.
Nice.
Thank you. Yeah.
Here we go.
And so this will be once this gets going, and if it's successful, this will be a game-changing view of the Earth's composition and the ocean. We're working on more accurate data about the gravity. So we have a gravity mission that's part of the Earth observing system that will be the gravity measurements we're making now are so sensitive that they can detect changes in seasonal amounts of groundwater or changes in single glaciers or glacier complexes in Antarctica. The new measurements will be another order of magnitude better than that. And so as you build that capability, the questions that you end up being able to answer expand remarkably. And then when you kind of link it with the time series of change, and then the integration that we have through modeling, through data assimilation, so we can actually get a comprehensive view of how the climate has been changing, but also enough information about the processes to tell you why it's been changing. So that's a work in progress, and we're getting better every iteration of this system. So you had your hand up first, and then we'll go to you.
Yeah. Okay. I had two questions. The first one is for soil carbon, like how you doing in terms of measuring the carbon in the soil. And the second one, because I came to watch the video on oceans, how are you also tracking for potential tipping points? Ooh.
Okay. Do you know how we're doing soil carbon?
No, we don't.
Okay, so soil carbon is a tricky one. Like sub-ocean temperatures, it's one of those things that we're trying to see whether there's a fingerprint that we can detect from space, but I'm not sure that we're there. One of the new ESO projects is to look at surface water. And it's possible that as we look at surface water in more detail, that we may be able to say something about what's in the water, which may give us some clues about how much interaction there is with the core. But I don't think we can look to space alone to get an accounting that would be robust enough for the global stocktake, for instance. But that's those are the kind of questions that we really want to. They're challenging us, right? Now the tipping points issue. So tipping points are they're not a theoretical concept, but they kind of come from models and theories where we say, we push it, oh my God, there's a threshold being crossed, and we see thresholds being crossed around the world in many different respects, whether it's sea level rise overtopping levees, whether it's the stability of glaciers moving past the point by which they're stable. There's always been this thought that we can look and we can get a head start on when something is tipping, but it's really hard. It's really hard, and while we're looking at a lot of the systems that we think have this kind of threshold behavior, the overturning stream function in the North Atlantic, the permafrost in Siberia and the other boreal regions, the West Antarctic ice sheet. We're measuring the health of those systems, and we're seeing the loss of mass in West Antarctica. We're seeing the degradation of permafrost. We're seeing the cooling in the North Atlantic. It's very hard to go from the measurement directly to a warning system that might be useful. It has to go via the models, it has to go via the projections, and making sure that those things are both coherent and robust is a huge challenge, but one that lots of us are tackling with. But I can't say that we've done that. Yeah.
Thank you so much for the great presentation. And this is really powerful in terms of early warning systems and even, getting vaccines out for livestock diseases. And what's sort of the next step then to upscale it to get, countries sort of using it and into the practice of really disease prevention? Thanks.
Do you want to
have a go? From the NASA perspective, we're providing the data. Right now we have 23 spacecraft that are constantly monitoring the Earth.
24.
Perfect. 24. And indeed, those observations are coming in, and we're doing a variety of analysis, and we provide a variety of data to our policymakers. So in reality, it's all about learning from that, the enabling ability that provides to negotiate, to provide aid and assistance where it's needed, because we can target those areas, as Ashraf really did a great job telling us about. So that's got to be a great step forward, the next step. So it starts with that fundamental research.
Yeah, let me add something to that. So, in order to provide such a practical benefit, you need to demonstrate that this is something that we can see, right, and that we can make, and that we can hindcast correctly, right? You need to be able to know what the false positive rate is going to be. You need to know, how many things you're going to miss, and so you have to look at the historical data, which we're gathering all the time, right? So historical data on disease outbreaks, that's not as well curated as satellite data, right? And so bringing those data sets to integrate better with the satellite data is one of our real challenges right now. So part of how we're moving our data operation is we're moving things into the cloud. We're trying to put things into coherent formats. We're trying to be able to make it so that things can line up with socioeconomic data, with health data, and it's really hard to get that to be all in the same place at the same time without you as a user having to download terabytes and terabytes of data just to find like a little thing. So part of the Earth observation system is we're starting now, before any of the satellites have been built, we're starting to build out a new a data set and a data infrastructure that would allow more of these things to happen, and then support the kinds of analysis where you're linking practical things that are happening on the ground to things that we can detect from space, and then finding the mechanisms by which it works. I mean, these things are not just correlations. It's not just machine learning has found a connection between these things. We know what the disease vectors are dependent on. We know that surface water is important for mosquitoes. We know temperature is important for life cycles of various parasites. Based on the epidemiology and the knowledge of the disease specialists, we're bringing this information to bear, without us necessarily all being medical doctors, right? So it's that kind of collaboration, and we're trying to build that out in a much more coherent and consistent way for users going into the future. Because I mean, we understand how difficult it is to use this data, and we're hopefully, if the president's budget gets passed and certain things happen, we're hoping to build out a new foci in our applied sciences program that would be very much focused on long-term climate decision making, and how the information that we have and the practical things on the ground can really link up together, and so we're going to be focusing a lot more on that in the years to come.
Okay. Another question?
This COP is about to produce. Well, so far, the meeting has produced two commitments: one on deforestation, and the other one is a new partnership on methane, tackling methane. What's going to be the role of the Earth observation community and the role of satellites in general? And what do you think is going to be the contribution of NASA? Is it going to be just inventing the widget on how to do greenhouse gas emission inventories? Or do you think there's new international partnerships that NASA wants to engage with in moving this agenda forward?
So this is a great opportunity to talk about how that might work. So right now, there are satellites in orbit that are measuring concentrations of methane, but they're not giving. We don't have a global picture. We don't have it all the time everywhere, right? And a lot of these satellites, there are European satellites, there are Japanese satellites, there are private sector satellites, and then NASA has two missions in the planning process: GeoCarb and Carbon Mapper, which is a collaboration with non-profits. And then there's Methane Sat, which is a US project but not a NASA project, where where all of these things are going to be looking at this kind of the methane elephant, but from different sides. So somebody's going to be tweaking the tail, somebody's going to be looking at the trunk, somebody's going to be holding on to the leg, and there will be a massive need to integrate that information by understanding exactly what it is that's being seen, exactly how it's being seen, when it's being seen, with what quality. And NASA, I think, can certainly be pushing to help that integration, using data assimilation, using our historic data that kind of looks at this a little bit, that we can validate against what we know has happened in the past. And we're working as well, in our modeling, to look at the impacts of changes in methane concentrations, not just on climate change, but also on air quality, the impact it has on ozone, the impact that the ozone then has on crop yields and public health and on aerosols. And so methane, is kind of, it's a fascinating scientific problem because it's reactive and it intersects with so many issues, including the aerosols that we mentioned earlier on. So you change the amount of methane, you change the oxidation of sulfur dioxide and nitrous oxides into aerosols, and so that changes air pollution in that sense too. And we're talking here with part of the Paris Agreement is kind of based on global warming potentials, right? So they're still using global warming potentials out to 100 years and trying to play off methane against carbon dioxide, which is a little bit tricky scientifically, as in not really scientifically coherent. And the work that we're doing at NASA is really we're trying to not just kind of dive into the impacts that changes in methane can have and the possibilities of win-win effects for both climate and air pollution and public health, but really trying to integrate all those different streams of data. And I think that if we can tackle that as a problem and take a leadership role in pulling that data together, pulling that modeling together, we can really make a big impact on the international kind of methane moment and things that we're doing. I think that's something that we should, as an agency, set our sights on and pursue with full force.
Yeah, indeed, the commercial sector is going to have a big play in this. Several groups are launching major constellations that will be making methane observations in the IR, which is a really critical frequency range to be able to detect it. And so a lot of that data doesn't necessarily have to come from NASA. We're going to be able to partner with whoever we can to be able to get it. And as Gavin mentioned, data assimilation is one of the key things NASA does all the time, every day, to be able to produce global products.
Okay.
All right. Well, thank you so very much.
Yeah.
We got several great Hyperwall talks tomorrow. Please check the schedule. We're going to try to jam a couple in between the best we can. Tomorrow's a really busy day. I hope you've all had an opportunity to pick up the book Earth at Night. It's free. I was privileged to participate in that, and I'll be happy to sign it if you'd like. Thanks so much.